Hey, welcome back. We'll continue. This is part two of the dry-in process. So let me start by kind of recapping where we were last time. And going forward, this is what where we're headed. I'll use the W boson production as an example, and we'll use the Jacobian peak and look at the W boson PT, and we'll find out that things get complicated because of soft gluon emissions, and that pushes us to do a resummation of that. And so I'll go through some of that and then look at the transverse mass distribution, which is also key for getting the mass of the W. And then the Tevatron is our reference, and LHC is moving on. So and what I'll be looking at, again, brilliant is the process is hadron going to a pair of leptons, but I'm going to decouple that. So I'm just going to chop that off. I'll focus on producing either the photon or the W, and then later you can decay that, and you can sort of break down the process like this. So I'll focus on this part, but then afterwards you can tag the decay, and the star means that's a virtual one, not necessarily on shell. So that's going to be the game. So we use W boson as an example, and one of the goals is to measure the W boson mass. So here's how you make W bosons. You do U plus D bar, for example, goes to W plus, and that goes to a positron and a neutrino. But the challenge is we can't measure it directly. It decays before it gets to the detector. And furthermore, we can't measure the neutrino. And as I mentioned last time, because the parton center mass frame is different from the detector center mass frame, we don't know anything about the longitudinal momentum. So it seems like there's more that we don't know than what we know. And what can we measure? Well, we can measure the PT of the lepton. Okay, we can measure the lepton PT. The longitudinal PT, we have no idea where that comes from, whether that's because, whether that's, coming from the parton center mass or what, but the PT should be invariant. That'll be invariant under boost, so we'll focus on that. So the question is, how can we use that to get at the W mass? And there's something in our favor called the Jacobian peak. And let me start by giving you a cartoon representation of this. So here's our, this is our beam axis, here's the electron going out. And just for a moment, let's suppose that the decay of the electron is uniform. So I'll work in one dimension right now, but here these right arrows represent all the possible angles where the electron can come out. Okay. And then what I want to do is using that, I want to get a distribution of the transverse momentum, the PT. So I've got these cyan lines going over here. And if you tilt your head, here's the plot of number of events for low PT and high PT. Okay. And you see, just because of the geometry of this, I've got a lot of lines up here at the maximum PT and fewer down here at minimum PT. Okay, and so that's the essence of the Jacobian peak. Now I've drawn that in one dimension. If you then, I can't draw it in 2 dimensions, but if you use your imagination and go out to 2 dimensions, you actually get another benefit factor there. And so what happens is, because of this geometry, if you map the PT, you'll naturally get a peak right at the maximum PT. And so if the W decays and the lepton and the neutrino zip off, carrying half the W mass, you'll have a peak basically at half the W mass. So that's the technique we're going to use. Now that you have the cartoon in mind, here's the math, okay? And it's called the Jacobian peak, just because if you calculate the Jacobian between the PT distribution and the angular distribution, you pick up this, factor in the Jacobian, and that's ideal because if you plot this, you get an edge. Assuming 0 PT, that's a thin line here, you get an edge right at where the at half the W mass. Okay, so that looks great, but then when you go to the experiment and try to do it, this gets complicated because it turns out the boson initially doesn't have 0 PT, There's some various things going on, some soft processes that sort of smear that around. And if you give it a small PT due to various sources, you get this red curve. So it's not quite as good, but it's a good start. We'll come to a better measurement in a moment. And the motivation, of course, of finding the W mass is one of the fundamental quantities of the standard model. Hence the PD distribution is important to measure in this. So we really want to get this right. And I'll just flash, here's a current set of measurements of the W mass. And you see, here's the standard model value in gray. And you see most of the things, they sort of scatter around them with error bars that sort of match, except for, this is a recent update. CDF did a very, very careful, very precise measurement of that, which you see is a couple sigma off from that, and that's an outstanding puzzle. There's been quite a bit of discussion and investigation into that. I won't dip into that. Maybe you can ask folks at the break. In particular, Pablo has looked at this and issues with the PDFs and uncertainties there, but that's an outstanding puzzle. But this is a fundamental parameter of the standard model, so we'd like to get it right. Also, if you put this together, I'm plotting here the W mass. On this scale, it's a top mass. There's 175, and that has implications for the Higgs mass. And they're all supposed to sort of coalesce here where the standard model prediction is. And things are sort of lining up, but not quite. And this is an analysis from GFITR putting all these together. So if we really want to test the standard model, make sure everything's behaving right, all these things should line up. And they're sort of there, but not quite, depending on which input you use. So what gives the W the PT? Because in the simple picture, we had two partons coming in linear with the beam, and they formed the W with 0 PT. Where's that come from? So here's an older measurement looking at the cross-section versus PT. And if you calculate what it is, it turns out you've got some excess events at particularly high PT. And what can happen here is if you just do your calculation of PT at some of the very highest regions, you're going to be low, and that's because you see this is a log scale. So I've got 1, 2, 3, 4 decades in the cross section. So this is way down in cross section. But if I have a little bit of smearing, of just a few, few hundred MeV, a fraction of a GeV, this is falling so steeply that if I smear this a little bit, I can, impact this, and just, on a very steeply falling distribution, I just push it out a little bit more, and it shows up there. So this is something we're going to have to worry about. And here, if I put sort of an intrinsic KT there of 760 MeV, less than a GeV, I can start fitting that. So, let's take a look at that. And if I want to calculate the full PT spectrum of the W, here's the data. It sort of looks maybe Gaussian down here, and then out here, it should be, this should, the events out here should come from a hard emission of gluon. So here's some of the diagrams that go into it. I can have a quark antiquark annihilation, okay, and then without the gluon, the W would have 0 PT. But if I kick off a gluon, if I kick off a hard gluon, then that can give me some sort of PT distribution. I can also have the Compton process where I have the quark and gluon, and that goes through and also goes through there. And so it'll be a combination of these processes. And somehow I have to put that together. Out here, I expect this to come from a hard gluon emission, but what about as PT goes to 0? Let's think about this as PT goes to 0. As that gluon becomes either soft or collinear, I'll have a singularity on this internal line. I'm going to get infinities. And so, here is the, if I look at the annihilation term, that's a dashed line, that takes off to infinity. I have something similar going over here with a quark, and that also takes off to infinity. So if I just calculate the next leading order result for this, I'm going to have infinity as PT goes to 0. Basically, I've got singularities like this, okay? And whereas it seems to behave more like a Gaussian, e to the minus PT something. So how am I going to get that out? And that's what we're going to take a look at. And if you put it all together, here's a cartoon. Paul will show this earlier, but the various regions of the transverse momentum distribution for this, if you're out at very high QT, that's where the perturbative physics dominates. So you expect to be able to calculate that by doing a hard gluon emission, and that should work. And then down here, if you're very low PT, that's where that's where we saw those 1/PT squared singularities. Something breaks down there, and so maybe that's some non-perturbative dynamics. Maybe there's some intrinsic KET, that is, the partons coming in. They're not exactly collinear, but the soft gluons that make them rattle around a little bit with a few hundred MeV. So we've got something down there, and then this green region is going to be a transition region where we sort of paste the two together in some sense. And if we want to get the full PT spectrum, we're going to have to put all these together. Now you can say, maybe I'll just work out here where things are nice and clean and everything's perturbative. But the problem is, a lot of the data is down here. And if I want the statistics, I want to be able to describe that region well. So that's the game. And to do that, yeah. Oh, sure. Yeah. Mm-hmm. Yeah, I'm going to show the CSS with the B-star description. I've got that figure coming up. So thank you. Okay. So what we're going to have to do, we're going to have to deal with all those regions. And a key part of that is dealing with those soft gluons. So this is the resummation technique. And so I'm not going to give you, the full lecture of that would be very long, but hopefully what I'd like to do is at least, sort of go from this where maybe it seems like a mishmash, but at least give you the outline or the basic picture of how that goes. So let's start off. Let's just look at the PT distribution for the W boson. We'll look at next to leading order. And let me just focus on the annihilation graph. Okay. So, if I just do QQ bar to W, that's everything's fine and good. And I get the Born cross section, that's well defined. But if I throw in that next leading order contribution with the gluon, because I can pick up this PT singularity, then I get terms like this. I get a log and I get a 1/PT squared. And if I try to take that to PT of 0, I'm going to get something not so good. So let's back up a minute and let's do this. Let's take this and let's integrate it over the full region, call it S, take S to be the maximum PT. I'll integrate this from 0 to S, okay, over PT. And then what I expect from that is I expect that should give me the Born cross section and then an order alpha S correction. That'll be my next leading order term. Okay, so that looks sensible. And now what I'm going to do is I'm going to split up this integral. I'm going to chop this in half. I'm going to integrate from 0 to PT, and then separately from PT to S. And I've just moved this over to the other side and written this 1 minus this quantity. Okay, so I've just, just mathematical manipulation. And when I integrate this, I've got a log here. When I integrate this, I get a double log. I get a log squared. There's factor 2 that comes in. And so this is, this is my cross section integrated up to a particular PT. So, if I go back to that diagram and say how much things are there between 0 PT and 1 GeV, 2 GeV, 3 GeV, that's my answer. And I've just done mathematical manipulation to say, well, you haven't solved the problem because you still have that singularity. I still have, when PT goes to zero, I've still got a problem. But now I make a great big assumption. I assume that basically this is the effect of a soft gluon emission and alpha S correction. And then at low energy, because when I go to low energy, alpha S is very big, I can do lots of those. And so let's assume there are lots of those soft gluon emissions. I can emit 1, 2, 3. I have a series. And let's assume this is the start of a series. And I say, gee whiz, that looks like an exponential series. So I'm just going to exponentiate that. Okay, and so, and you can see if I expand that out, I get this term, I get that term. And when I write this as an exponential, this is problematic, but once I wrap that as an exponential, I've got an exponential of a negative quantity, that's going to be well behaved. And so in a nutshell, as I say, oversimplified, but in a nutshell, that's the idea. We're assuming that exponentiates. And so here, what we've done is to essentially make an assumption to resum those series. Furthermore, if I just differentiate that to get back to the PP distribution, here it is. I get this term, and that's what I had before. That's a problematic term. But then I have I have this, and at PT of 0, that nasty singularity is going to be suppressed by this negative exponential. Okay, and so if I just do the next leading order, I've got problems. But if I assume that exponentiates, that exponential will save me. And so here's the cartoon of what I've got. I've got an exponential of a minus alpha S log squared. So let me just write L for that log. I've got exponential minus alpha S log squared. And then here's the, if I expand that out, here is the assumed series that I'm doing. And I have alpha S log squared, that to the second power, third power, etc. And that's what I've done. So these are the soft gluon emissions that I'm assuming we're picking up. So I've skipped over a few details, and let me put in some of those details now. Okay, these are just a few of them. We summed over only the leading logarithmic singularity, but it turns out we need to do better because of the convergence and perturbation series. That's because the expansion is not alpha S log, it's alpha S log squared, as we'll see. We assume the exponentiation, and the proof of this is non-trivial. And so, the problem here is when you have multiple scales, you get 2 logs per loop, and you've got to deal with that. Also, the gluon emission was assumed to be uncorrelated. It turns out that leads to too strong a suppression at PT of 0. And so we have to have some way of opposing momentum concentration to PT there. And then in the limit, PT goes to 0, the alpha S argument can go to 0, and that leads to infinities. So I've got to do something here. I've got to, handle this non-perturbative region, and that'll be the B star prescription. So this is just, as I said, just sort of a overview roadmap, but let's take a look at these 4 things one by one. So as I said, we summed only the leading logarithmic singularity. Okay, and so that was an exponent of alpha log squared. And if I expand that out, I get, for every power of alpha, I get 2 logs. So I have alpha to the 1 log squared, alpha to the 2 log fourth, etc., etc. All right, and what am I missing? Well, you can figure it out. I have alpha 1 log squared. What I'm missing is alpha 1 log. And here I have alpha 2 L4, alpha 2 L3. Okay, and if you compare here and here, you see these terms are only suppressed by alpha log, not alpha. And that's a problem because if that log is large, I mean alpha S, let's say it's 0.1, if that log gets to be of order 10, your perturbation series won't converge at all. So somehow, if we could sum both the log and the subleading log, that would be great. So let's pretend we can do that. If I exponentiate not just the leading log, the L squared term, but if I pick up the subleading log, and I expand that out, then I get this. I get a log in 1 and L to the 3 and L to the 2, et cetera, et cetera. And now when I compare, okay, when I compare, I see the terms I'm missing really are fully down by alpha, not just alpha log. Okay, and so if I could do that, then this would give me a convergent series, even in the case of large logs. And so that's one of the first steps that we have to deal with. Okay, we assume that the exponentiation is works out, but the proof of this is non-trivial. And I'm not going to go through that. Let me just show you where the logs come from. And I'll go back to the one scale problem, but we sort of take care of that with the renormalization group equation. And then for a 2-scale problem, the extension of that was done by Collins, Soper, Thurman. The shorthand we refer to it as CSS, and that puts those together to actually pick up 2 logs, and that's one of the cute tricks that makes this feasible. So first of all, where do the logs come from? And so I pulled this from the CTEQ handbook. This is the total cross section for E plus and minus at 3 loops. And so here it is. I've got a forward cross section. I've got a 1 and alpha S and alpha S squared somewhere. There it is, alpha S squared, alpha S cubed, and stuff. So, it's pretty ugly, but that's 3 loops. And you've got some, ugly functions in here and constants, but okay, that's for 3 loops, that's not too bad. Part of that is because I only have 1 mass scale. And because I have 1 mass scale just from dimensional analysis, I can't have, ratios of things. I can't have any Q dependence in here aside from the alpha S because, there won't be anything to cancel it out. Let's take a look at something that does have an extra scale. So if I have a Q and M squared, for example, this is Drell-Yan at 2 loops, I've got my reading term, and then I've got all this stuff, and I've got lots of logs of Q squared over M squared and some ugly functions and lots of logs. This is only 2 loops, but it is a whole lot more complicated, again, because I have the extra scale. Okay, and I have 2 masses that allows me to introduce logarithms. It gets much more complicated. So let's go back to the renormalization group equation. And basically, if I have 1 scale, say Q, and I've got my renormalization scale mu, I can make ratios like this, Q over mu. Okay, but now when I have an extra scale, I have Q and QT, I have 2 combinations of logarithms that I can make. Now, the renormalization group equation, oversimplified, is to say that physical observables should not depend on that renormalization scale, and so I can just apply to the chain rule for this. If my observable depends, if I've got the scale here in the alpha S mu, just doing this out, I have the differential with respect to mu, and then the alpha dependence. That's basically the beta function. Okay, and the beta function tells you how the alpha S changes with the mu scale. Okay, and then what you can do is you can apply this, and if I expand this out, say in powers, if I do a Taylor expansion of this, I've got alpha S squared. I've got things like log of the scale plus possible constants and log squared log constants, things like that. But because I know how things vary with mu, because I know that information, I have the freedom to choose mu where I want. And this was discussed previously in the lectures. So as I say, to oversimplify this, what I can do is I can just tune mu to be Q. All these logs vanish, and here's my new result. All the logs vanish. I've got some constants to deal with, but in an oversimplified sense, I just sum the logs. So if I only have a 1 scale problem, I can use the freedom of the renormalization group equation because I know the mu dependence. I can use that to take care of the logs. But what about when I have more than 1 scale? So if I have, if I have not just Q, but I have Q and QT, you can't do that because you have logs of Q over mu, logs of QT over mu, And especially if they're very different, you can't knock off both of them at the same time. Yeah.
But already at one scale, the whole belongs to the vanish. Like
Sorry.
even with one scale in the previous scale, the all belongs vanish always.
As I said, I simplified it, but you've got to make a dimensionless combination.
Yeah.
And if the only physical scales are, if you have Q and mu are the only combinations, it's a one scale problem, then you can use that to minimize the logs. So,
Okay.
yeah.
Sometimes I don't know, in group computation, you have more complicated functions, whatever polygon.
Right.
How do you take care of that?
Well, yeah. So I mean, for the simple case, you have, you know, for the one loop, you've got just, you know, logs, but when you got polylogs, again, I mean, the only dimensionless ratio you can make is Q over mu. So that's what it's going to be, and you can tune that to, you know, minimize or to make sure you're in a reasonable area. What's challenging here is, in particular, what the interesting region is, if you're doing MW processes, the Q is around MW, and now we're interested, a lot of the data is down at low PT. You know, if I'm doing high PT where QT is similar to, you know, it's up around the mass of the W, then I can put mu in that ballpark, the logs will be small. But what I'm really interested is, I'm interested in the low PT region to, you know, get that, you know, the Gaussian behavior where a lot of the data is, and now Q and QT are going to be different. So, yeah, and then for the higher cases where you get polylogs and things like that, you saw those in the two-loop Drell-Yan case, some pretty ugly functions. Yeah, you have to figure it out, but the only dimensionless ratio you have is Q over mu. And so, you know, you can vary that. You probably want to, you know, minimize the higher, you can tune that to, you know, as Pavel, he talked about the principle minimal sensitivity, you can play that game or things like that, but you only have one ratio. Here are two ratios, you can't play that game anymore.
Yeah, I mean, like, if the explanation, like, exact, or like, you always have some place for the pen, even after the RGS.
Okay, I guess I mean, so you only, I mean, in terms of dimensionless quantities, everything can be represented in that. So, you say your question again?
Like, so you do your analog computation, but then you do the other things, try to
Yeah.
results. But then after you do that, is the resolution like is the log dependence concept exactly, or like you still have even after playing some kind of residual state dependence?
Yeah, I guess I'm not, you know, I'm not sure quite where you're getting at, but yeah.
Yeah, okay.
No.
Yeah.
Yeah.
Thank you.
Yeah, no, that's specifically why I put the disclaimer oversimplified up there. Yeah, in one slide, it's hard to get those things in. Yeah, so coming to this again with a high level view, we use the renormalization group equation, which says that the physical cross section doesn't depend on the mu scale. Okay, and that trick it allows you to choose your mu value to kind of tune it to keep. You've got a single dimensional ratio Q over mu. You tune it to sort of get the best perturbation theory. You can't do that with two scales, and this is sort of the genius of the Collins-Soper-Sturman approach. What they realized was not only do you have the symmetry of the renormalization group equation, you have gauge invariance. Okay, and they set this up in a particular way. They decide to use axial gauge, okay, with an axial vector, call it the psi, and then you have this, you can dot that into a momentum, okay, and basically then your gauge invariance, the fact that the cross section doesn't depend on the gauge invariance, you can write that like this. D sigma D this is 0. And you set that up in the same manner as you did for the normalization group equation, and that gives you a second set of relations that you can use to take care of the second law. Okay, and that's the short version of it, but it's elegant to use this symmetry to sort of handle one log, this symmetry to handle the other log, and yeah, that was the insight that allowed us to do these two scale problems. There's so that was you know, step 1 and step 2 that I covered. The third thing I skipped over, we assumed gluon emission was uncorrelated. But for example, you could imagine a set of gluons where I've got the W boson at 0 PT, and a gluon gives it a small kick, this you know, a small PT, and I sort of assume that, you know, the PT just kicks it farther and farther away. If you assume those are totally uncorrelated, you'll get a depletion at PT of 0. And, you know, here's a cartoon, but you could have, you know, one kicking it away from PT of 0, the other kicking it back. So you have to basically put in the momentum conservation here. And so the way that the Collins-Soper-Sturman did it, basically you have this momentum conservation. They implemented it in B space, and they basically an impact parameter space doing a transform. I think there have been some attempts to do that without the B space, and there have been some. I'll refer to the one older one, and there have been some more modern ones. But again, this solves a problem that you get too much of a depletion at PT at 0. Finally, the last problem is we encounter non-perturbative physics. And in that exponent, I'm integrating from max of around Q down to some low scale. This is in the B space. B is inverse to the energy. And the problem is I'm integrating down to very low scales. The alpha S is going to be non-perturbative. Okay, so I've got to cut that off in some manner because the alpha S will blow up. And there are a number of methods for doing this, but one method is to use the B star prescription that sort of cuts off B max, which puts a lower bound of that scale. And then it sort of protects that lower integral. But what you're doing is you're cutting out the non-perturbative physics. So if you do that, if you have your exponent integrated over all B, you're cutting it off at all scales. You're cutting it off at low scales. So you're missing out on the non-perturbative thing. So you have to add that in. And so you've got to do that in some way. Where you cut this off depends on the non-perturbative function. So if you choose different ways of cutting that off or different prescriptions, you'll have different non-perturbatives, but you've got to put that in. So those are the 4 steps that I sort of skipped over, and here is a brief but incomplete history. Here's the original Collins-Soper-Sturman, some implementations, one by some folks here, and then here was an effort by Ellis to do the QT resummation, not in B space. There's been more since then, but I haven't referred to it here, and some other updates. So there's been quite a bit of work on that. So let me just recap where we've been. So we summed not only the first, but we summed the 2 leading logarithmic singularities. That was the exponent at alpha S L squared plus L. And by picking up the leading and also the subleading, that meant our perturbation series was ordered by alpha, not alpha times the log. And so that was critical to get the proper PV behavior. We assumed it exponentiated. Okay, I sketched the ingredients. And the key ingredient was use the renormalization group equation to essentially vary the mu to control one of the logs, but then you have a second log. What do you do about that? There you use the gauge invariance, and they use a very clever form using the axial gauge, and the axial parameter then took care of that. And then the gluon emission was assumed to be uncorrelated. So at least in CSS formulation, they transport that to B space so they can impose momentum conservation in B space. And then in the exponent, you have to integrate down to a scale of 0. So you cut that off and you introduce a non-perturbative function that you have to fit in some way. So those are some of the details there. And when you're done, here's what you get for the cross section. This is transformed into B space, but basically you've got your cross section here, and then you've got your exponent of your log, and then your non-perturbative, where this is a Sudakov exponent, and it looks something like this. It's an integral. I've got a log here and a constant, but when I do that integral, this will turn into a log squared, and that's a log. So again, this I probably should. I think I should have dropped an alpha in there. But basically, this is the L squared L, and that's what I use in that cartoon notation. And so what we've succeeded in doing is summing this infinite set of gluons in a manner that is well controlled and pervasive good. And I've left out a lot of material, and to say a lot, I think that's a understatement. So let's put it all together. So we have our sum calculation, okay, and here it is in cartoon form. It's the leading part. I've got exponent of alpha s L squared L, and if I just expand that out, then I get basically this. And I get this, and so here it is expanding out order by order. It picks up this term. I pick up 2 logs at this order, 2 logs at this order, et cetera, et cetera. And then the perturbative result, the perturbative calculation, it gets the Born part, and then it picks up all the logs at this order, but it doesn't do the next leading order, 0. And so if I just take those two and add them up, you see I've got a problem because here, this is good. I'm picking up these terms, but I'm double counting here and here. And so if I just add those results together, I'll be double counting some contributions and not others. And so what we're going to do is we're going to take this perturbative result, take the asymptotic limit, and pick off these particular logs. And so what we'll do is we'll subtract those out. And I'll subtract those out, and if I take this plus this minus this, that removes the overlap between the two. Okay, and again, just to step back, the resum result, that was very good, and the limit of the QT was small because we're picking up all those logs. But the perturbative result was good for the larger QT, where QT was order NW, and we don't have the problem of those soft gluons quite the same way. And so the full result is going to be the combination. I take the resum result plus the perturbative minus asymptotic. Okay, and again, this is clearly a cartoon, but versus transverse momentum. Here's the perturbative result. Okay, and I expect that to be a good representation laying out at the large QT. But when I take PT to 0, that's going to diverge because it's got the 1/QT squared singularity. The asymptotic result is basically the expansion of this, so it matches out here, and it goes, is regular down there, and then the asymptotic is cyan. The asymptotic result is taking the limit of PT that goes 0, picks out the singular parts of the perturbative. It may or may not go to 0, so typically we have a mechanism to turn this off at high QT where we don't want it. But basically, this is going to be what subtracts out the perturbative, so that at low QT, where I expect the resum to be good, the total goes to this. And so basically, the full cross-section will be an interpolation. Down here, I want the resum result. Out here, I want the perturbative result. And then there's a little bit of freedom in how you put that together. But the net result, putting all that together, allows me to get the good representation for the cross-section. Whoops. Good representation of the cross-section across the whole space. Okay, and again, coming back, this is a figure, Pavel made, and so this is another representation of the whole thing. I've got on here, I've plotted this. I've got an extra power QT. That's why it's going to 0 versus this one. But again, this is the full representation. And using this, I can then get a full good representation across the whole range. And so you saw this one before. This is the D0 data, the CDF data. And again, with the this is using the LY function fit for the non-perturbative part, and putting that together, you get a good representation for those. Okay, so let's return to the measurement of MW, change it up a bit. And one of the challenges we had there was the PT seemed like a good variable, because we could use the Jacobian peak. But then as soon as we put in a little bit of smearing, say from soft fluence or things like that, adding some finite PP, that smeared things out a bit. So let's try a different technique, and we're going to use the transverse mass. So before I start with the transverse mass, let's just do the invariant mass. If I try to compute the invariant mass of the W, okay, it decays into an electron and neutrino. So if I were to add up, basically add up this, that would give me the invariant mass. But I don't have, I don't necessarily know the longitudinal parts of this. So the best I can do here is take the transverse electron, the transverse, well, the neutrino I'm going to have to infer. But basically, this gives me the transverse parts. So it's not the invariant mass. I'd like to use the invariant mass, but it's the best I have, given that I only know the transverse components. Okay, and so I can also express it like this. But one nice thing about the transverse mass, in contrast to the PT, is that the invariant mass is MT is invariant to leading order. And if you want to show in some exercises this evening, you can verify the definitions of NP are MT are this, and also if you do this, you can verify that the MT is invariant to leading order than PT. And so that's good if you have some soft gluon messing this up. This is a better measure of the W mass. So on the top, here's my PT. Okay, and then here's my transverse mass down here, and this is the problem I showed you before. If the boson has exactly 0 PT, you've got a nice sharp edge here at half the W mass, and you can use that to nail the W mass. But as soon as you add a little bit of smearing from soft gluons and things like this, you get this, it smears that out. Whereas the invariant mass it's not quite, sorry, the transverse mass is not quite the invariant mass, but it's close enough so that when you start smearing it out with finite PT, it does rather well. There's still, in the yellow, there's some detector effects you have to put in, things like that, but it does a better job. So, all right. So that's sort of the tour. A lot of the results I showed you were from the Tevatron run 2. That's the past reference. And there's, as I show this, an outstanding question about the W mass coming from the CDF reanalysis that has to be figured out. And if you like, we can discuss that this evening. The LHC is happening now, and the high Lumi LHC will happen going forward. So again, that's quite relevant. But these general techniques about the resummation, PT distribution, things like that, apply to a wide variety of things. Yeah, so here's again, just the recap. That's a puzzle. That's a whole lecture that I'm not going to get into. But those are the sort of puzzles that are interesting, and by solving them, you either find new things or you learn other things. So here's just a few older slides from D0 showing, for example, missing ET, the transverse mass, the PTW, and yeah, you see that's from a while ago. And again, this is the updated with the G fitter. So all these things come together, and if the standard model, if all there is a standard model, it should somehow center on the standard model point. And you can take a look. We're getting there, but the question is whether there are small deviations and things. So is still an outstanding question. So where we've been, yeah, the W boson mass is important, but the Jacobian peak's a nice approach. But you have to worry about the soft gluon emissions. And then we did a roadmap of resummation, a high level tour. There's much more to get into, but hopefully that gives you an overview of some of the techniques for dealing with multi-scale problems. And there's a whole nother set of multi-scale problems with quark masses, the heavy quark mass, and you heard a little bit about that with the PDFs and the variable flavor number scheme. And then the transverse mass is an improvement over the PT distribution, but putting those together, particularly for this puzzle we have with CDF measurement MW, we'll have to figure out what's going on because it's a fun one to look at. Let me just thank many of the people who I got help from or stole slides from listed there, and a few references. Again, sort of the books that Pavel recommended, and also you can look back. These CTEQ lectures are on the web, so appreciate that. And yeah, go out and calculate. But I'll leave it there, and thanks, and have some time for questions. Everybody's good. You're all set to do the summation? Yeah.
Before you do the
All right.
Can you go before you leave the review?
Okay. Is it on the first slide?
That is the first. You can make a logarithmic, maybe make an expansion, and you not cancel the exponential and the logarithmics.
Yeah, was it the renormalization group right here, or?
There, no, here.
Here?
There you have an exponential of a logarithmical and just cancel these things out instead of doing the
Cancel.
exponential from the natural logarithm.
Yeah, I've got, I mean, that's just typically the W mass, and then PT, I mean, the infantry, particularly where PT is small. And so the problem is those scales are disparate. And so my logarithm is not going to be, my logarithm is going to be not small. Yeah, so I mean, those are physical scales. And if I'm interested, if I'm interested in the high PT region where PT is close, S is going to be on W. If I'm interested in the high PT region where PT is close to W, those laws aren't a problem. And the fact that my expansion is alpha S log, that's not a problem anymore. But the problem is when I go to PT, I have two very different scales, MW and PT is small, then that log is going to be big. And if that log, well, that log is bigger, that log is bigger or comparable to alpha S, all of a sudden that perturbation expansion doesn't conversion. And so that is the two scale problem, and that's what Hans Sturman figured out how to take care of using basically the gating trick, which I think is quite elegant. And this trick here, I've given the reference, but it was Jeff Owens that showed me this trick. But the original papers, the Airbury and Dogshitzer, they did this trick to sort of rearrange the terms and set up the resummation. That's not a proof of the resummation, but if you believe these manipulations are valid and you believe I can exponentiate that series, then all of a sudden I've taken something singular and I've got it into the Gaussian form. And the Gaussian form sort of looks like, what the data was seen here. And so I'm not sure, that was before my time, but they may have seen that data, said, how do I get a Gaussian out of this? When you do that manipulation, that gives it to you. So, is there a question? Is there any other form of resummation that doesn't rely on X? Yeah, all the ones I know use the exponentiation model. I'm not sure if anybody else wants to comment, but yeah, as far as I know, that's that's the trick. You know, whether you're semi-soft gluons or whether you're dealing with heavy quark masses or things like this, basically it's the logarithms that are giving you the challenge. And you sort of saw that when I showed the Drell-Yan 2 loop. It's the logarithms that are giving you the headache. And so those are the guys you have to deal with. So yeah. Sorry? No, I don't, yeah, I don't think I don't think the insertion of color matrices is a problem. So yeah, as far as I know, and again, I think you can solve it, Saul sort of showed us you do the soft color connections and things like that to fix up the color afterwards. So I think those go through for all the cases I know. Right? Yeah. Maybe we should talk about that. That's way out of my area, but I do know. The problem with this looked at, one of the questions is the way they do PDF insertions, and a number of us think that's one area. The other things I don't know about. You want on the PDF? You want to comment about the video? Yeah. This was a decade after they finished the run, so they spent a lot of time. The presentation online, the presentation was about an hour, but I think, well, I tuned out after the second hour, when they went the second hour questions, they were not shy. They took all questions and answered all questions. So they're not hiding anything. There'll be enough time about what it is. So if you can see where the difference is, you're lucky. Nothing else. Let's go ahead and take a break. And we do want to get a picture in. So I think we'll either do a picture after Saul's lecture or after Kieran's lecture. We'll look at the letter and figure that out. So we do want to get a good picture. And any other messages? No, I think that's the sign up for the. So that would be, if you want to go the old.
We've got the break of, well, basically we're asking it's $55. If you go to the old museum, we get more than that. So, therefore, I'll pass it out the sign up sheet. Please consider it, but I need to be over to the downtown to pick them up around 12 o'clock. We can get to it. It takes about 40 minutes to be walking from the old pole. Then you go to the museum first, and then you go to the downtown, go walk by the river, and you hike around as well.
And tomorrow, we was training today, but tomorrow's supposed to be nice and clear. And we suggested, if you take a 12 o'clock bus, that means you can sleep in the breakfast and catch, food at 11 in the cafeteria opens. And then, go downtown, Sunday afternoon downtown and you're there, that's good. Yeah, so if you're interested in that, the full price is 10, but if you get the group, we'll make it 5. If you want to sign in, so we'll pass that on.
Yeah, and certainly on Sunday will be very important here. There's very important to like for our type of like.
Coffee time.
Your notebook 3 relies on your Google Drive.
Which one?